So the schedule for all those assignments we have laid out at the beginning of the course. You guys have done a great job. We have been moving along very nicely. I may want you to do the homework assignment because it would be better if we do it before your midterm 3. So that homework assignment will be due on the 27th. And then we're going to have the third midterm exam Wednesday after the Thanksgiving. I saw some of you might need this already, but some of us, some will test problems. I do want to remind you guys though, ultimately, if I can give you guys a suggestion, is going through the lecture material and then using the homework assignments or the sample test as a way of, reinforce your learning. But ultimately, going through the textbook material, understand the principle and foundations and go from there. Because as you know, for one particular postulate or principle, there's a lot of questions that we can come up, right? Also, the second one is we only have 50 minutes of a test. We didn't cover every single component of the material. So, if you miss, okay, so therefore at this stage, you guys are mostly junior and senior level, so you know how to study. So I just want to give, because otherwise, you're going to say, oh, this doesn't look like what I have for the homework problem. It is. Or the practice, right? So go study. Yes?
Could we get an extra day on homework 8?
Is there a reason behind it?
We got
Is
tests
it you?
Thursday.
Is it just?
I had like 3 tests this week, and so I had no time to work on it.
Yes, I think that's exactly what I considered at the beginning of the course when I made my syllabus. Because I job how many? 2, exactly, for this specific reason, because it happened to me too. Sometimes things come up, I just want to job the lowers. So I give you guys those freedom. So, and utilize that. Feel free to utilize that. But if they are special, there's no special. Actually, totally forgot. Because of that policy, and it has to be fair for everybody. Alright. Okay. I do want to touch bases on this, because I do consider, and that's the reason I made my syllabus for job, because I couldn't just go all 3 midterm and 1 final exam. So you can take those opportunities if you would like to, either to something. You guys at this stage and all busy. I can't think of one single person. Maybe some of you who are not busy, raise your hand. Every one of you are super busy, different classes and researches, and maybe some part-time job, maybe have family, right? All of you guys are busy at this stage. So, okay. Right, so the last part of the thing for this one electron system that I would like to touch base with is the spin, right? So we discuss one electron atom or ion system. We investigate the motion of the electron, or the electron motion in the atom. Actually, the one electron atom is only the hydrogen atom. The mostly ion, let's say helium, you can have one make and one electron. It's a positively charged ion, you have to lose one, right? So you have a lithium 2 plus, that is the one electron system. Now to understand the motion, because we only have one electron, so therefore our wave function only depends on one position for that electron. So you can use R as a factor. And then, this is a motion in 3-dimensional space. So in that regard, you can define that motion of that electron either using the Cartesian coordinates or spherical coordinates. So xyz or r theta phi to refer to that position coordinate for that one electron system. Now, we come up the wave function, we went through it, and know a wave function that are defined by those three quantum numbers, right? So we come up the variables, we went through the Schrodinger equation, and we come up the wave function exact expression. You have three quantum numbers here. Now this describes the orbital motion of the electron with respect to the nucleus. Okay. Now the electron also have spin. Right. So the electron also has spin. And you can consider spin as an intrinsic property of the system, which is the electron here. You know, can you think about other examples of intrinsic property of the system? Mass. It's like a make you. Another example would be gas, right? So you can consider the spin, although it's more complicated than this, but you can consider this is just an intrinsic property of the system. Right. Now for electron spin, you guys learn from Chem. You're going to have what kind of spin the electron have? Electron spin. When you learn from Chem, when you a lecturer told you, basically we're gonna have what do we call that one? Spin up. And then we have an arrow as spin down, right? That's what we learned. Okay. Alright. Now, we said we have an angular motion, then we have a quantum number L. What is the definition of L? Orbital. Momentum quantum number due to the orbital motion of that electrons. Now, what are the quantum number values? L can take 0, 1, 2, 3. Of course, we restrict the value of the n values. Now, we can think about the z component. So this is really the z-axis of your orbital angular momentum quantum number. Okay, now I give you a special name. This is really your z component. Or what do we call it? Give a special name. It's a magnetic quantum number, right? Okay. All right, that was just a review. All right, now due to the orbital motion, what about the magnitude? So what is the magnitude of the angular momentum? How do we know? You know, we have a linear momentum, we can calculate the value, we can have an angular momentum. Now how do we know? How can we calculate the magnitude of the angular momentum? That equals to, you link with your quantum number, root of L times L plus 1 h bar. Now how about the z component? M sub L H bar. Alright, everything is just a review. Now the electron have a spin. So equivalently, we were going to introduce a spin. So electron has an orbital motion, also have a spin. So equivalently, we will also introduce a quantum number associated with the spin. Now, you already probably know we will use a lowercase s to indicate that quantum number, the spin quantum number. Okay, now the spin quantum number for fermions, for example, the electron is a fermion. Then the spin quantum number value will take a different way that you're doing for orbital momentum. We're not going to dive into deep. For a fermion, the spin quantum number for the electron is a half integer, 1/2. Okay. Now, the spin also have the spin magnetic equivalent to the orbital motion. You have the z component, and then you have a spin magnetic. We will do the same thing. The notation is m sub s. All right. Now, how are we going to take the m sub s value? The same idea. How do we take the m sub l values, guys? You found the negative L, 2L, and you have all the step plus 1. Then the spin magnetic quantum number, you will do the same. What are you going to do? You take it from the negative s, go all the way to positive s, and then you're going to have all the steps, if possible, between those two. You guys follow me, okay? It's the exact same way. Now, what do we have in here? What do we have for the spin value? 1/2. So therefore, you can think about 1/2. The limit is positive, negative 1/2, positive 1/2. If you do this plus 1, you get exactly 1/2. So in that regard, when you have a spin equals to s equals to 1/2 for electrons as a fermion, then the spin magnetic quantum number only have two values, positive 1/2 and the negative 1/2. Okay, now let's take it one step further. We link them all together. So when you learn in Chem, you say it's a spin up. All right? Which means the m sub s, it's no longer just a spin up anymore. We can put it into the spin magnetic quantum number as 1/2. When you have a spin down, that is corresponding to the spin magnetic quantum number negative 1/2. So we link them, the descriptive fashion of it, together through continuation. Okay, sometimes, for the L, we can also use letters to represent, right? So the orbital angular momentum number, we say 0, 1, 2, 3. We can also do S, P, E, F. Okay, same thing. If you say MS equals 1/2, we can use a letter notation symbol alpha. The same idea. And if it's a spin back down, you can do beta. All right. So that gives you an idea that to give you a whole picture of the description of that one electron in a such system, we will have two components, guys. One is the now if we piece them all together, if we look at such system, the total wave function only have one position vector for the electron, which we know that position vector for define the electron, we use the spherical coordinates r theta phi. Now that total wave function has two components. One is the orbital, and the other one is the spin component. Yeah? Yes? Now, what about the wave function for the orbital, which we already derived? Those defined by those three quantum numbers as r theta phi. That is your wave function solution for the orbital motion. As we derive, you will have a principal quantum number, orbital angular momentum quantum number, and the magnetic, and r theta phi. That's what we just discussed. Now, what else do we have? You multiply by the spin. So therefore, if I say the electron is in the 1s orbital, then this wave function will become C100 or C1s. But to come up the total or complete wave function in that wave function, then we need to consider the spin component too. Yes?
Could you try writing in a different marker? Just really hard to see that last part.
This one?
Yes.
Rewrite it?
Yes, please.
We can't see the markers.
It's a little faint.
Oh, yeah, it's reflected, right? Okay, good. Yeah, that's a good stopping point, because I was going to ask you guys to jump in something. Alrighty, it's a problem. I think none of them. Let's see if we can dim this light a little bit better. Does that help it out, or is it worse? Right now.
It's a little better.
Alright, here we go.
There we go.
Can you see this here? Alright, so this will equals to two components, the orbital component, and then you need to multiply by the spin component. So let's say, give an example. Let's say the electron is in the 1s orbital. What would be the total wave function equation, guys? That will have the product for the the orbital component, 1s, which corresponding to 100. At this point, and everybody know what 100 is. You guys agree? Now, how about the spin? So, the spin for the electron either will have a spin up, which you multiply by the alpha, or that electron in the 1s orbital could also be spin down. So therefore, you can have this orbital in this fashion, or is that clear? Because the total wave function for the electron have two components. We had a lengthy discussion about the orbital wave function. Now we just need to add in the spin component, and the spin has the spin up and spin down. So if you take a look at this one, then we know the total wave function will depend on the quantum number n, l, m sub l, origin from the orbital component. And then you need to add the fourth one, which is your spin. So the total component of the wave function is a product of the orbital component multiplied by the spin. And the spin for one electron either have a choice of up and choice of down. Now, whether it's up and down, it depends on the particular system we're taking a look at it. So therefore, I'm showing for you an example. If it's a 1s, you have the orbital wave function 1, 0, 0, which we know, and you multiply by the m sub s, can be alpha or beta, or you can just, you don't like letters, just say 1 times 1/2 or negative 1/2, that is fine. Yes?
So when you say multiply it by alpha or beta, do you literally just mean like a half or a negative half, or do you mean by the magnitude of the spin?
So if we take a look at this, are those quantum numbers or magnitude? Quantum numbers, right? So therefore, this is referred to the quantum number of what? M sub s. Now, what m sub s we can get is the magnetic component. It's a quantum number. It's not a magnitude. So you can calculate the magnitude through the quantum number. Those are two different things. I hope that clarifies your question. All right. Okay. Wow. This is that is the last slide for the 8A, and I just went through. I know the slide is just like one slide, but we went through the whole board because I just want to give you guys as much as I can to help you with learning. Okay. Okay, now let's move on. How do you guys feel? All good? Yeah, okay. All right, now let's move to the you guys can study hard, but also need to take care of yourself. This is a season people can get sick really easily, right? My daughter just called me this morning, she's sick. So I told her to get some vitamin C. So you guys really need to drink a lot of water, take care of yourself. Okay, all right, school is important, but in my opinion, the health is the number one, right? So you guys need to learn how to take care of yourself. Okay, all right, so what journey do we have here? What do we start? Oh, don't worry, I'm immune to all the viruses. All the time. That's not what my concern is. But I just want to, it just reminds you, I'm a mom, so therefore, I just want you guys to know. That's why I tell my daughter, you can work hard, but the health is your number one. All right, what journey do we have in so far? We started with the postulate, right? That's the foundation. And then what do we know? That's a whole series. The foundation, the series. Then what do we know is we apply. Right? We have the same set. We applying to different systems. So far, what did we apply to, guys? We have the translational motion. We apply to, can you see, not every time I write something, you can't see. Vibrational motion, what else? Rotational motion, right? So if you think of a system and particle, it could have those three motions. Translational motion means moving in the space without rotation, right? And the vibration you already know, and the rotation you already know. So those are the three motions. And then what do we do? Hopefully, I have 7 of them. So hopefully this is This is a much, yeah. All right, what else do we have is the Oh,
Whoa, that's much better.
you know, if you guys get rich, if you guys get rich, I know, right? Right? So, if you guys feel rich and you really like me as your instructor, and you want to send me a gift, you guys know what to do.
Markers.
Marker. I need to tell our main office. Ryan, tell Trisha. Like, I got this from our main offices, you know. Alright. So then, I'm not going to rewrite any of those, but translational, vibrational, and rotation, and then you bridge into the hydrogen atom. Or, this is so much easier. I want to keep it. Way much ions. Right? But look at the periodical table. Right? What do we have? The elements have the atom has many electrons. Okay?
She says come see her, she just does something.
You're not focusing, class? Alright, so many electron system. Alright, and then what else we want to do is molecules. And alright, so we already accomplished. Great job, guys. Up to here. Alright, really great job. Okay, now we're gonna discuss about many electron system. Can you give me an example of a mini electron atom?
Lithium.
Huh?
Carbon.
Carbon. Okay. What is the simplest one of mini electron?
Helium.
Helium, yeah.
Huh? I want to go. Carbon is great. Carbon is great. Nowadays we are really interested in carbon in so many different ways, right? So what is the simplest? That's what we always do. We have something we start with most simple. So what is the simplest one? Helium. Okay. We will do the same. We will understand the electrons in the atom. In this case, in the helium atom, how many electrons do we have? So therefore, we ignore the motion as we do for the hydrogen atom. Right? We just consider the motion of the electron in the hydrogen atom, and we take the same strategy. We were interested in those two electrons. All right. Now, how do we approach a quantum mechanics problem as we study from translational, vibrational, rotation? What is the general idea? How do we do it? You need to have a model, right? The model can be a free particle in a box, a harmonic, a simple harmonic oscillator, or a free particle rotation on the sphere. So you need to have a model. Now, based on the model, what do you get? The next step.
Here.
You guys know it. You guys know it.
Mhm.
Then you can generate the Hamiltonian operator. Afterwards, what do? You plug it into the Schrödinger equation, and then we'll give you the solution for the wave function as well as the energy. Now, once you know the solution for the wave function, guys, you guys are so powerful because we can do so many things based on the postulate. You can calculate so many different things. Is that true? Okay, now let's write out. What do you know what we need to write out? The Hamiltonian operator for the electrons in the helium atom. I'm going to give you guys 2 minutes to think about this. Right? Maybe 1 minute. The Hamiltonian operator has 2 components for the system, right? So what are they? Always. Because the Hamiltonian operator is the operator for the total energy of the system. Now, the total energy of the system consists of the kinetic energy and the potential energy. So therefore, the operator for the total energy also contains the operator for the kinetic and the potential energy. Now you have to think about what do I have? So if I usually like to do your diagram sketch so that can make me feel better or understand this better. So this is your nucleus. All right, now, I'm just saying, here's an electron, one of the electrons. I say electron 1. Do we have another electron? Can I just put it here? Electron 2. So this is a 2-particle system. Right, so 2 electron, so this is a 2-particle system. If it's a 2-particle system, guys, how many position vectors do we have?
2.
2, right? Because I need now the idea for us to understand the electron in the hydrogen atom, we take the origin at the nucleus, because we want to investigate the motion of the electron with respect to the nucleus. Since the nucleus is so much heavier, we think it's stationary. So that is our foundation. So therefore, this is really, if you really look at it, this is your origin. Now I have one position vector. I can use a label to denote that is position vector to one of the electron. It's just, you guys have the idea, so I'm not going to add anything more to make it, not needed complication. And then I have another position vector. That's a variable. It depends where the electron is. If the electron is here, it has a value, and there, and a different value. But basically, you will have 2 vectors. So in that regard, then my Hamiltonian operator will have 2 position vectors to describe these 2 electrons. Now, each one of them, if I really want to write out, then each one of them, the position vector, consider the a set of x, y, z. So the I is a vector in 3-dimensional space. Then you have x, y, z for one of the electrons, then x, y, z for the other electron. So if we take a nutshell, if you look at that, this is a how many variable system?
6.
Have you guys solved in your life a 6-variable mathematic equation? It's
Yeah.
hard, right?
Yes.
Isn't it hard?
Linear algebra.
This is literally a 6-variable mathematic equation. All right, now what else I can have is I can have a distance between those 2 electrons. I can denote the radius, the distance, with R12. So the R12 is define the distance between those 2 electrons. You guys all good? For this, I can also use the repetition coordinates, but if I write out what we're doing, we can use R1, theta 1, phi 1, that's one set. For the variable positioning R1, then we have R2, theta 2, phi 2. So now we're using a spherical coordinates. All clear right now? Okay, now let's get right out the expression. So I will have a kinetic energy. So then the motion of those 2 electrons, because I have a nucleus, electron 1, electron 2, we consider nucleus is stationary, so therefore we don't want to worry about it. So we didn't worry about the kinetic energy for the motion for the electron. Now how are we going to come up with operator? So that is the operator for the kinetic energy component for that electron. All right. That's a good stopping point. Does that make sense to you? What is the del here? Del square.
All of your derivatives.
Del square is the partial second order, right? Partial derivative in the x, y, z. Now and the system is your mass of the electron. So therefore, you need to add another component because you have the second particle and you have the kinetic energy operator associated with the second electron. Because it's with respect to the position, this position is not the same for the electron 1 and 2. So therefore, that operator you need to differentiate. Although mathematically it's the same operation, but with respect to different variables associated with that electron. Do you have any kinetic energy component? You guys, I just mentioned to you, those are referred to the variables of electron 1, electron 2. Okay, so that concludes our two components of the kinetic energy, right? Okay, now how about potential energy, guys? Last time, I remember, you guys want me to put it into the potential energy for electron in the hydrogen atom in the equation sheet?
Yes.
And you said there's no potential energy expression in the equation sheet? I think we do. What do we have in here?
Have a Coulomb.
Is that in the equation sheet?
Yes.
Is it?
Yes or no?
The Coulomb? Yeah, okay.
Is that in the equation sheet? Then that's, no, but do we have this one?
Yes.
Okay, then I don't need to change anything. Okay? Is that true? Because otherwise you guys want me to give you this guy here. Alright, now let's look at the potential. What kind of potential do we have? We have electrons that are negatively charged. We have another electron negatively charged, but the nucleus is positively charged. So then you have charged particles in the system. Now, exactly what kind of charged particle scenario do we have? We were going to have the Coulomb potential between the charged nucleus to one of the electrons. Then we also have the Coulomb potential between, same way, the second electron. That true? What else do we have? We have, now with many electron system, you no longer have one electron anymore, you have many electrons. We're going to have you also have a Coulomb potential between electrons. So when you have two electrons, so the only electron 1 and 2. So that is conceptually that I want to think about it, and then I need to plug into the expression. Alright, now let's consider the Coulomb potential between your nucleus to the electrons. This nucleus is your helium. Now we say this is your generic expression. Now what do we have it here? One is the charge on the nucleus for the helium, so it's a positive charge carries 2e. And then times the other particle is your electron carries one fundamental charge, but it's negative value. Then you're going to divide it by a constant. We don't really care the same. And how about the distance? What is the distance? If I consider this your electron 1, it's the distance for the electron 1 to the nucleus. Now what is it? Oh, excellent. Great. Excellent. Okay, very good. Now what else do I have? I will have the same thing for the nucleus to the electron 2, same fashion. So the charge is still from the nucleus, 2 fundamental charge times -1 for them the electron. So this is your nucleus charge, this is your electron. Now you divide it by the constant and time the
R2.
distance for the second electron. to the nucleus, which is
It's R2.
R2. All right, very good. We're not done yet. What else do we have?
30 electrons.
Yes, so the charge, so that is a -1. Excellent. -1. Then the 4 pi epsilon 0. Now what about the distance?
R12.
Yeah, very good. That's it. That's it. So therefore, you will have a 6th variable, right? And for your Hamiltonian operator, depends on those two positions for those two electrons. If we use the spherical coordinates, we can have the r theta phi. Each set define the position for one of the electrons. Then the Hamiltonian operator separated into two components, the kinetic energy plus the potential energy. All right. I always like to challenge you guys because you guys are great. Now let's take a look at this. All right, let's take a look at this, okay? Take a look at this guy. If I combine those two together, what does this look like? This looks like this white electron atom system, isn't it? For the hydrogen atom, or white electron system, what do we have? The definition of the kinetic energy plus the potential energy. Is that what we did? So this really looking like the Hamiltonian. Oh, I need a. If I combine those two together, this looks like for the Hamiltonian operator for one of the electrons equal to the kinetic energy plus the potential energy for the electron to fill the nucleus. Same idea, this guy and this guy is looks like the Hamiltonian operator for the second electron. You know what? You better ask Trisha to order whatever number of lectures that I'm going to have. This is already ruined, okay? So the electron tube. Did you guys see this? Did you guys see this one? Did you guys see it?
It's okay.
Then what remains? What remains, guys?
Electron interaction.
So now what do you have? Okay, so the Hamiltonian operator to define those two electrons, we write out the exact, but if we take a look at this, you can have the Hamiltonian for the electron 1 as itself, occupying the orbital, plus the Hamiltonian for the second one. What is the addition? What is the addition, guys?
The electron.
What is addition?
The electron interaction.
Is the
There's a lot of
electron interaction. That's really cool, huh? Alright. Now, what do you guys think? Do you think that we can solve for this algebraic equation, get it exactly function?
That'd be hard.
Alright. Okay, now, who said carbon? Alrighty. Now, maybe one of the testing exam, can you guys write out the Hamiltonian operator for your friend's question for carbon atom?
No, thanks.
No.
No, you guys can.
Well, we can,
Right
but
now, it's exactly the same. You have 60 electrons, so you have 6 kinetic energy term, right? And then you can think about each electron to the nucleus and the cross interaction for sure. But I don't want you guys to take your 50 minutes just to write out that Hamiltonian
Yeah,
operator.
maybe give us lithium or something instead.
This is, yeah. Okay, you guys heard it, okay?
Oh, no.
You know. Alright, so basically, this will be really cool. If we can solve it exactly, that's what we're doing it, right? 6 variables to function. But it reached the stretch. We may solve for this one, but the next one, we won't. So that's not what we're going to do. So what we're going to do is we do based on quantum mechanics, but we bring in approximation. Right. Okay, that's the one part. The wave function of many electron atoms, what we're going to do, as shown in here. So to solve for the exact, then that wave function will carry exact or dependent on all the position vectors for how many electrons you may have. But that is too complicated to solve it. Alright. Now what we're going to do is we're going to bring in orbital approximation. Now what does that mean? Instead, the wave function depends on all those variables and solving for the exact solution. We bring in the approximation, which is the product. You can consider each of the electrons occupied in that one particular orbital, and you multiply those atomic orbitals together for how many electrons. So therefore, instead of one wave function depends on all the variables, now each electron has its own orbital wave function. Does that make sense to you? Does that make sense to you? Okay, all right, cool. Now, how do we understand the electronic structure? How many guys heard this like in the electronic structure something? It's really fancy, right? So what does that mean, guys? Like when people say electronic structure, so we say electronic structure of this hydrogen in many electron system. Now we will have to like a fishing expedition. So when we say, I want you guys to we want to know what is the electronic structure of the many electron atom. What is really looking for? Because sometimes we have a problem with like, okay, I don't know what it is. If I know what it is, boom, I got it. And that's where each discipline has its own terminology. I'm sure when you tell me something you're learning in your field, I'm like, I don't really know what's going on. So therefore, for us to learning a new discipline, new field, new something, make sure pay attention to those terminology. So the electronic structure is really showing you the occupation of the electrons in those atomic orbitals. Now, after we said this, I'll let you guys go. Let's say I have a helium atom. What is the occupation of the electron in the helium atom, guys? In the ground state. The 1s.
And then 2.
And then that's your atomic orbital. Population of the atomic orbital, and you indicate superscript 2. That is the one way to report the electronic structure. And that's what we're going to carry today. When? Friday? Wednesday?
It's Wednesday.
Yeah, all right. So good. I can see you guys soon.